Okay, we're very happy to welcome Masanori Hanada here, periodic physics, and he'll tell us about numerical tests of case gravity duality. And dinner will not be tonight, it will be tomorrow. The organizer will be Juan, who is communicate directly with him. The place meets 6 in the lobby, or?
Yeah, 6:30, let's say.
6:30 at the lobby.
Send me an email so they have it come.
Okay, thank you for the invitation. So today I talk about the numerical test of the gauge gravity duality in D0-brane matrix model, which I've been working for a long time. And there are some new results. And if you can take only one message to home, then the most important message is that there is a talented young physicist applying to the postdoc this year. So in case you see application document, maybe you will. And not working.
So just look there once and then start working.
So today, so we want to study gauge gravity duality. And gauge gravity duality relates black hole or quantum gravity to non-gravitational systems like a matrix model or super MLs. In principle, we can use this duality to non-perturbatively define quantum gravitational systems, otherwise very mysterious beast. So I want to study this side, which is at least, this side, we know at least in principle how to define. And maybe we can study the detail and see how mysteriously black hole appears. But in principle, how can we study non-gravitational system theory? It's typically we have to study strongly coupled regions, so this is a non-trivial question. And one possible answer is use the numerical simulation. Non-gravitational theory is a kind of cousin of QCD. And in the case of QCD, there are a lot of effort in a lattice QCD community, and the numerical method is pretty successful. For example, this is a plot made based on result by PAX, Schwarzschild collaboration in Japan, and the BMW collaboration. BMW here means Budapest, Marseille, Wuppertal, which is a European collaboration. And they independently succeeded in reproducing a low energy hadron spectrum very precisely. Here, these 3 points are input, but just using that input from experiment, they could reproduce mass of other hadron. This way, it's possible to check that the QCD actually reproduces experiment. And maybe using such method, we can solve QCD very precisely or solve standard model very precisely. And if we see tiny deviation from there, we can claim that we found the UFIs. And maybe we can
sorry, what kind of fermions did they use to reduce it?
Here, you mean, so here, up, down, and strange are introduced. And you mean like
just implementation on the lattice?
Implementation on the lattice. It's 2007, so probably they use the staggered fermion or Wilson fermion. And physically, they say 2+1 flavor, up, down, plus strange, and other heavy ones are not implemented. And maybe we can do something similar for matrix model or super MLs. And in this case, instead of experiment, we can compare the result with gravity. And if we can solve a matrix model or super MLs precisely, at least numerically, then we can do non-trivial test of the duality. And maybe we can confirm the duality or falsify the duality. Or maybe just using, by solving the matrix model or super MLs very precisely, maybe we can find something new in gravity side, which we don't expect just based on something we know in gravity side. That's what I want to do. And the specific setup we study is a duality between black P-brane, in type 2A or 2B string, and P+1 dimensional supermil. And this P, when this P is 3, this is ADS5 CFT for correspondence, but the P does not have to be 3. So it can be non-ADS, non-CFT correspondence. And on the right side, for P of 0, 1, 2, and 3, we know how to define the theory, at least or lattice. If P becomes larger, it's not very clear how to define it on QHD side, but at least for P equals 0, 1, 2, 3, we can define theory and we can study. And today we will focus on P equals 0 for the reason I explained later. But there are also serious effort in P equals 1, 2, and 3 by many people. This is the outline of the rest of the talk. So first I want to show the numerical result on the confined phase of the D0-brane matrix model. And I want to compare it with the type 2 superstring. And the argument is very good. So we can do very precise test of the duality. And in the second half of the talk, I want to show some evidence for unexpected new phase, which is confinement phase. And I want to give you some speculative proposal that this confinement phase can describe M theory. So this is a Lagrangian of the D0-brane matrix model. So we have a coupling constant here, and this Xn is a n by n Hermitian matrix. And there are fermions, and there are 16 supersymmetry. This is a dimensional reduction of 4-dimensional maximal super MLs, or 10-dimensional n equals to y MLs to 0 plus 1 dimension. And it appears in various contexts. In 1995, we pointed out this can describe the low energy dynamics of the D0-brane and strings. And a bit earlier, in 1988, Louis Hoppe and Nicolai obtained this model when they tried the matrix regularization of supermembrane in 11 dimensions. And because M theory and membrane are related, after this, people realized that it may describe M theory. And Banks, Fisher, Schenck, and Susskind proposed this model as a non-compatible formulation of M theory in certain cases. And Itzaki, Maldacena, Zonesha, and Yankilovich gave more standard aviation CFT like correspondence between type 2A D0-brane and this model near to 53. And this proposal related to type 2A and M theory consider different energy scale, which I will mention.
Sorry, are they the same limit or different limits?
Different limit.
Different limit.
So M theory is stronger coupling and lower energy.
With same Lagrangian with different limits.
Same Lagrangian, but different, yes, energy relation. And so there are various people involved. So maybe using BFSS, just a specific name from a specific paper may not be very fair, but I want to use this name here because we also have to consider BMN matrix model, which is also the D0-brane matrix model, but one parameter deformation of this. So let me use the BFSS model to specify this. And when I say BMN model, this is one parameter deformation of this. And both are D0-brane matrix model. And what I want to show today is analogous to so-called 3/4 problem in 4D n equals to 4 supermills. If we calculate the energy density in 4D n equals to 4 supermills as a function of the Hooft coupling from and we consider Hooft limit, then from Hooft counting and dimensional counting, n squared times t to the 4 appear. And then with coupling, we can calculate the overall question. And I don't precisely remember, but let me use C here. And after strong coupling, if we believe the duality, then we can use gravity to estimate the energy. And we get something very similar up to 3/4. And if we take into account the perturbative fraction at weak coupling, it goes down to B. If we calculate the 1/λ correction based on the alpha prime correction in string theory, it goes up to B. And people hope that somehow they're smoothly connected because we don't really expect any phase transition in between. But solving this theory at the generic coupling is of course not easy. So this is strictly speaking, conjecture. And numerically, in principle, we can interpret these two, but the numerical simulation for these supermills is still challenging. But for the case of the D0-brane matrix model, we can solve essentially the same problem. And that's what I want to show today. And this is a paper by Sunny and Fuan and Kobe and Shimon. Okay, so they consider the generic P plus one dimensional mills and D0-brane, but we focus on P equal to 0 today. And in 0 plus 1 dimension, forced coupling has a mass dimension of mass to the power 3. So this is dimension 4, unlike 4-dimensional theory where lambda is dimensionless. And this lambda, it can be regarded as something defining typical energy of the theory. So it's analogous to lambda QCD in some sense. So whether energy is high or low is measured in this unit. And if we take energy of the system, lambda times e to the minus 3 gives natural dimensionless coupling. And if we look at this combination, if lambda large and e small are essentially the same. So low energy is essentially strong coupling in this theory. And if you look at this paper, they show the precise dictionary between matrix model and back to a string theory. And we can calculate the energy of the system by using a black hole solution, black D0-brane solution in a gravity side. And in supergravity limit, energy is 7.4, or it is 7.4 is some curriculum number consisting of pi or some other numbers. It's a 7.41 something, times n squared, which comes from the put counting, times strange power parameter and t to the 14 over 5. Because lambda is dimensional for, we cannot really do simple dimensional counting here. Because strange power can appear. And if we believe the duality, we expect the confined phase is favored at any non-zero temperature. And the energy, by the confined, I mean the energy is order n squared. And if we calculate the Pareto group, this is Pareto group is non-zero. And from here on, I want to set lambda to be 1. And if you want lambda, get back lambda, then you can just introduce appropriate power lambda so that the dimension. Okay, so at the strong coupling, we expect supergravity. So here, this is energy divided by n squared versus temperature. Low temperature is strong coupling. High temperature is weak coupling. At the low temperature and large n, we expect supergravity should give a good approximation. So we think we expect that mass of the black hole should be the energy of the system in gauge theory side. And at weak coupling, we can rather easily estimate energy divided by n squared is 6 times t in this case. Because it's weak coupling, we can do such calculation. And at the high temperature, so if we get precise result from matrix model, at the high temperature, energy should approach this line. And at low temperature, gradually simulation results should go close to this line. That's what we expect.
To get the 6T, do you get effective masses for the modes at high temperature?
Let me remind how to get to 6. Basically, this is you just count how many degrees of freedom exist. You just use equipartition.
I know, but naively they're massless, non-compact. They're not harmonic oscillators. I was wondering if somehow you turn them into effective harmonic oscillators.
Because action is so you have p squared and also commutator squared, which is a power x to the 4th. Yeah. You can just use Villar theorem, and if you apply Villar theorem, this 6 should appear, if I remember correctly. Yeah, after the talk, if you give me 5 minutes, probably I can do it. I cannot immediately do it. But there is only x to the 4th term, and there is no other term to simplify the formula. significantly. Okay, so let me see how historically the simulation was improved. So these are the first simulations in 2007 and 2008. I say the first simulation, but the first Monte Carlo simulation, which is analogous to lattice QCD. And back in 2001, Habata and Lifshitz tried to apply some other approximation method. Okay? And they got some at least qualitative good result. The Monte Carlo simulation started in 2007. And this is our result. And this is by Cutler and Wiseman. And here, instead of energy, they plotted energy divided by temperature. So instead of 60, they have 6. Okay. And this dashed line is 60 plus some pattern of the correction. And both of us could see a nice approach to high temperature recoupling result. And at finite temperature or finite coupling, we see clear deviation from a recoupling result. And then approach to supergravity is observed. But this, we didn't take Lagrange limit and we didn't take continuum limit. Okay.
Sorry, can you explain again why one of them depends on T and the other doesn't?
So this is energy, and this is energy divided by temperature. So that's the only difference. So y-axis is different.
But it's the same. Is it the same?
Yeah. So here, so at the high temperature, we should get 6 times T. Here they divided by T, so they get 6. It goes to constant.
And the rest, if you just process it by changing T.
If we multiply T, then we get more or less the same result. And our result looks cleaner, but because in the paper by Cutler and Wiseman, they plotted 2 kinds of data simultaneously. And these circles corresponds to the data which didn't suffer a problem associated with the flood direction, which I will explain later. And these squares are data points which suffered from flood direction. And if you remove these points and just focus on these circles, actually they are floating slope. Okay. Anyways, consistent result was obtained. But at this point, this wasn't large and this wasn't continuum. And in 2008, we improved the result a little bit. We went a little bit larger n, and we went a bit closer to continuum limit. This lambda is, so we used the introduced the momentum cutoff to study the system, and this lambda is momentum cutoff. So larger lambda would mean
continuum limit. Why do you call it continuum limit?
Continuum limit. So we're doing thermodynamics. So we have imaginary time direction, and it's a compact phi to the circle. And along that direction, we introduce lattice point momentum cutoff. And we have to take a continuum limit for that imaginary circle.
This is continuum limit in Euclidean time.
Yes.
Space
is just a point, so there is no continuum limit needed to that direction.
But the target, there's a
time,
space in the
imaginary time.
Yeah, but there's a non-compact target space, which is the actual space.
So there is no space, only time. Yes. In the time direction, we take continuum limit. So it's a one-dimensional lattice. Or in this case, we didn't use lattice and we introduced momentum cutoff. But we just have one Euclidean dimension, which is time.
And what n is the end of the matrix, or n?
SU n, matrix size n. So SU 17. And that was the largest value we could study on the specific computer we are using at the time. There is no deep reason for that. So people say n equals to 17 looks like a prime, so there must be some reason, but actually there's no reason. Anyways, and this T to the 4.6 corresponds to first alpha prime correction. And the fit looked good, so we were satisfied at that point. But then 7 years, almost 6 or 7 years later, Kado and Kamata used better supersymmetric lattice action to study this model. And they didn't take large n, but they went to larger n, and they studied a bit wider temperature range. And the result look pretty similar, but if when they perform similar fit result look inconsistent. And if we plot them together, there is some subtle difference here. And that subtle difference leads to big difference in fit of the alpha prime correction. But still at this point, we didn't take Lagrange, we didn't take continuum limit. So clearly, the lesson here is unless we take Lagrange limit and the continuum limit, we cannot say, we cannot do precise test of the duality.
What does continuum limit here mean, since n is all there is?
So we have SUN matrix model, and because we are doing thermodynamics, so this is zero matrix model. So it's 0 plus 1 dimensional theory. So this is space, and this is time. And as Nati said, there is no space, so we don't have to take continuum limit regarding space, but we take the imaginary time, and the size of the circle is 1/temperature. And you can imagine that we introduce lattice points on this imaginary time circle, and we have to take continuum limit along this circle.
The first paper you worked at fixed end, but you didn't try to extrapolate to n to extract them.
Yeah, so we thought the n equals to 14 and 17 is very large, and we couldn't study many different values of n, so we didn't large and limit at that time. But what we did.
Sorry, how do you treat the fermions? I didn't understand that. So
I will, yeah, I have a slide later, but this comes up, essentially we use a method used in lattice distribution. So this simulation takes into account fermion. Okay, so in 2016, so we used a much better computer, and we switched the action to some different action so that massive parallelization is possible. And we studied the very large n and many lattice points, and took large n from the continuum limit. And I will explain how we did that. And yeah, and this is from 2016 paper. We got this point in purple color. And this year we added a few more points at low energy. This is also large n continuum. And we can see clear approach to supergravity line here. Okay, and if we zoom in here, strictly speaking, here we use the BMN matrix model, not BFSS matrix model. We have one deformation parameter equals 0.5, but this is very close to BFSS. Okay, and this solid black line is gravity prediction for BFSS, and you can see some dashed line here, very close to the black line. This is a gravity prediction for BMN with this specific flux parameter. So the difference is much smaller than error bar, so we don't really care the difference. And then this data point is very close to this, and this tiny deviation can be understood as alpha prime correction. And you may think somehow error bar is very small here and error bar is very big here, and there is a reason related to the second part of the talk. So I will explain the reason why here we have bigger error bar, but focus on this beta point. So this is 0, and this value is like 0.22 or something, and the difference is very small. And so it clearly supergravity is emerging at the low temperature. And I want to explain how we made that plot. And probably many people in this room didn't really do Monte Carlo simulation by yourself. So let me just give some short introduction of the Monte Carlo simulation, just to tell you the flavor of the work we did. Okay, then I will explain how we got that result and how we got that fit. The Monte Carlo is a name of this rich people's neighborhood in Monaco, and famous for casino and Formula 1. And the reason why it's called Monte Carlo is so during World War II, the Manhattan Project, von Neumann and Ulam came up with the idea of using a random number to do simulation. But it was, of course, classified information, so they needed some code name. And then their friend, Metropolis, said maybe Monte Carlo is good because Monte Carlo is famous for gambling, and using random number sounds like gambling. And also, if I remember correctly, Ulam had some relative who loves gamble so much and borrowed money from him and went to Monte Carlo or something. So Monte Carlo was funny to them. So that's the reason the name of Monte Carlo was born. And at that time, Las Vegas wasn't a big gambling city yet. So if it were a bit later, then it could be the Las Vegas simulation. But at the time, Las Vegas wasn't gambling place. So this is called Monte Carlo simulation.
Question.
Right.
I have a question.
Hey.
Yeah, so the supergravity limit that you're talking about, you just have
yes.
You just have one data point which tells you that the energy scales in a certain way, right?
So
but for the action of the supergravity, what about the spectrum?
So here, what we did was, so this supergravity should be good description in a low temperature limit, a strong coupling limit. And the final temperature effect is in string theory side, it's alpha prime correction. So actually, this orange line is a fit which takes into account alpha prime correction. And it's consistent with the string theory expectation. And for this fit, actually, we didn't use only these points, but these points are also used.
No. What I'm saying is, I mean, how do you know that you're reproducing supergravity, especially because you're just getting a certain curve which maybe matches some features of supergravity. But if you're saying that you're reproducing supergravity, you should reproduce the entire action, right? In a certain sense.
So the precise statement is, so this is one particular observable, which is the energy of the system. And we did these data points. And those data points we obtained is consistent with the result from supergravity plus string correction. So we can just say it's consistent. We cannot say we derive supergravity. And as you said, we can calculate out of observable as well, and we can do more precise tests, if you like. Okay. Here we are talking only about this specific quantity. So in that sense, I shouldn't say we derive. We see our result
so it's just consistent with what you expect from supergravity.
Yes.
That's what you're saying. Okay.
Well, I mean, he's saying that the energy you have coincides with the energy you
yeah. But still there is a small deviation, and that deviation is consistent with the supergravity. And no, a string theory. Anyways, so Monte Carlo simulation. So I don't have time to explain the detail of the Monte Carlo simulation. So just to give you some basic idea. So we want to do, let's consider field theory for a matrix model on the Euclidean space with the action S of phi. So here matrix model has only time, but we consider imaginary time. So it's a Euclidean theory. And if we can generate field configuration with this probability, exponential minus s divided by z, then if we collect many configurations and take the average, we can reproduce Euclidean path integral. And in Monte Carlo simulation, or more specifically Markov chain Monte Carlo simulation, we generate such field configuration with this specific probability weight. And of course, here there is one big assumption. So here, this weight exponential minus s has to be positive. Otherwise, it cannot be probability. Okay, and in some theories, it can become negative, and it's called the sign problem. But if we don't have a sign problem, we can use the Markov chain Monte Carlo method in principle. And in Markov chain, there are many algorithms, which is called this name, but all of them make a sequence of configuration. So phi 0, this is the initial configuration, and then we slightly change it and make the first configuration, second configuration, third configuration, and so on. And once configuration is given, then the probability that some specific configuration appears as a next configuration, it's described by certain transition probability. And if we choose this transition probability appropriately, we can realize the probability distribution we want to use for Euclidean path integral. And the choice of algorithm is a choice of the probability distribution. And let me explain the simplest one, Metropolis, just to give you some flavor. And in an actual simulation with the fermion, hybrid Monte Carlo or rational hybrid Monte Carlo, which are more complicated, I use, but the basic idea is very similar. It's just some technical complication. And if you want to know the detail, you may think I'm trying to sell my own book, but actually you can freely download from universities. So yeah, and here I gave a basic introduction to these books, so you can just download. Even if you download, I don't get extra money, I suppose. So it's sad. But if you read, I'm happier. At least. I don't know. Maybe I can tell you the rating, but
how about both? That would be the nice.
The editor said if we can make more than 1,000 euros, that's the kind of best seller. Almost nobody can make more than 1,000 euros. Anyways, let's make the simplest example. Metropolis, and we apply to Gaussian integral. This is the most trivial example that has all the essence. So Metropolis algorithm is actually a proposed Metropolis and 2 Rosenbrothers and 2 Taylors. So by 5 people. And but it's too long, so it's called Metropolis. And let's consider Gaussian integral. So we take action to be just one variable function, x squared over 2. If you want to consider QFT on lattice, we just have more variables. And this action becomes more complicated. Okay, and the partition function is just this integral. And if we want to generate a probability distribution, exponential minus s over z, what we do in Metropolis algorithm is just change x a little bit. This delta x is some random number between minus 0.5 and plus 0.5. Okay, and this is a candidate of the next configuration. And then we accept this as a new configuration with this probability, or reject otherwise. Okay, so with some probability, new configuration is obtained. With some probability, old configuration survives. And we just make the chain longer and longer. And just by using this, so this defines the transition probability, and that with that transition probability, we can show that correct probability distribution is obtained. And if we take the initial value of x equals to 0 and just apply this, and then this is how value of x changes. So this clearly it's fluctuating around 0. And if you count, how many x fell into which range and make a histogram with 100 samples, it's very far from Gaussian distribution. But if you have more and more samples, clear convergence to target distribution, which is Gaussian distribution in this case, is obtained. And we just do it with many variables. That's a lattice QCD simulation. And if we plot x squared instead of x, we get this kind of history, and we just take average of them. And then if we plot this average, so let's take a sum of first n x and divide by n, or take a sum of x squared for first n configuration and divide by n. If this n goes to infinitely large, convergence to analytic value is observed. And in this case, of course, we know what is analytic value, but in the case of matrix model or quantum field theory, we don't know the value, but they just use the same algorithm and we get the right answer. it's guaranteed. And if we start with, and I used x equal to 0 as the initial configuration because I knew that x equal to 0 is a peak of the distribution. But if we don't know the distribution precisely, then maybe we start with some stupid value like x equals to 10, which is far from the center of the distribution. But then we see quick summarization here, and then values start to fluctuate around the peak, which is 0 in this case. And then we just discard this and take average, take this part to calculate observable. And the important thing we can see from here is after this initial summarization process, configuration with a small weight would mean x too large or too small, they never practically appear. And we just pick up x, which is dominating the integral. So in this way, after the summarization, all the important configurations which dominates the path integral is sample. This is called the important sampling. And thanks to this important sampling, we can save the computational cost significantly. And this, we just repeat the more complicated version of this for more complicated integral. That's a Markov chain Monte Carlo simulation.
And try to improve sampling using machine learning.
There are such, yes. So I say algorithm amounts to the change of configuration. And for this step, like I said, you know, in what I showed now is I just added some random number, but maybe you can make a neural network and feed X, and the neural network returns X prime. And then you do, for that candidate, you do some, this kind of test. And that way you can improve. You can change this probability, transition probability. And of course, what I said is a bit simplified, but basically that's what people do. And by improving this transition probability by using, for example, machine learning, we can see a much quicker convergence to correct the distribution. And in order to introduce a fermion, we use the fact that in most cases of interest, including our case, fermion appears in bilinear form. So here, so action is written as a bosonic contribution plus fermion contribution. The fermion part is cyber times Dirac operator times psi. Okay, and because it's bilinear, we can just integrate the fermion by hand. And we get the determinant. And we just take this, interpret this part as a probability and apply similar algorithm. And of course, once we have determinant, calculation of determinant is very costly. So Metropolis doesn't really work. So we have to improve it. And hybrid Monte Carlo, or rational hybrid Monte Carlo is suitable when we have determinant in the probability distribution. So essentially, we just use this effective action, which is a bosonic part minus log of determinant of D as a probability distribution, and generate bosonic field configurations. And then we can calculate the various observable. And again, crucial assumption here is, the determinant of D, so exponential of minus SB is usually real, positive, but the determinant of D may not be positive. If this is positive, we can use Monte Carlo method. And there is some subtlety in the case of supermills, which I will explain in this slide. Anyway, so Monte Carlo simulation is doable by using a technique from lattice gauge theory, which is in the end, very similar to Metropolis algorithm. It's just some technical improvement. And also, we focus on p equals to 0 because if we have a positive p, there are many lattice points, then simulation becomes more costly. That's the only reason. Okay. And if we have just a 0 dimension, we don't need too many lattice points. And then instead of, because volume or number of points becomes smaller, we can make n larger, which is crucial for the test of the duality. And the subtlety, which isn't completely understood is a science problem. Actually, determinant of D, that part can take a negative value. But when we can correct, there is some way to think with the account of effective phase, although which is very costly. And whenever we can do that, we can check that the phase doesn't really contribute at all. Just using the absolute value of the determinant instead of the determinant, somehow we get the right answer. And that's numerical observation, and we don't know why that happens. But at least numerically we know that, so we just forget about the phase factor and use the absolute value of the determinant. Okay, this is called the phase range. We work on
Question.
this. Hi.
So this D of A could have 0 modes, right? I mean, this D of A, I mean, the determinant of D of A, the D of A could have 0 modes.
Good. So in a case of finite temperature, actually, we don't have 0 mode. And it depends on boundary condition. And for the talk today, there's no 0 mode. And when there's 0 mode, you have to take care of that 0 mode. For example, you take out the remove 0 mode. Otherwise, the partition function is 0. But for today, at the finite temperature, there is no 0 mode. And that's related to the antiperiodic boundary condition for fermion.
Oh.
And for example, even if you use a periodic boundary condition, there can be 0 momentum coming from fermion. Fermion 0 mode exists, but if you take the J group to be SUN and not UN, probably for almost all configurations, determinant is non-zero. Anyways, and we consider metastable bound state of all D-branes. And I want to explain this part, which is related to so-called fraction.
Okay, so when you regularize the time, so like time is a lattice for you.
Yes.
And then how do you regularize the action?
I will show that this action later.
And will you have supersymmetry that action?
That action we use breaks supersymmetry, but in continuum limit it is restored.
How do you know?
First, intuitively, in the case of 0 plus 1 dimension, there is no UV divergence. So because of that, rather naive action can work. And if you want to be very precise, including non-perturbative effect, you should check like Ward-Takahashi identity, which should become identically 0.
This action has relevant operators that violate supersymmetry.
The lattice action we use is, I also showed the joke slide, but I hope you didn't see. Yeah, this is lattice action we use for 0 plus 1 dimension. And perturbatively, we can show that there is no SUSY violating contribution at continuum limit. And also, at the non-perturbative level, some numerical test is needed. And typically what we do is check some identity which should hold when supersymmetry exists. And we can numerically show that in continuum limit, such relation is actually reproduced. And I hope you didn't see joke slide. Anyway, so it is fine. Or maybe if you're worried, we can discuss more. I'm not worried. Okay, result is right, at least. And so point here is that, okay, so we have a commutator square term here. And if xi and xj all commute, then potential is 0. And that potential is not lifted when we have a supersymmetry. And so by just taking diagonal configuration, we can take eigenvalues to infinitely large without costing energy. And if we take into account such configuration, actually partition function is divergent. And eigenvalue of matrices can be interpreted as a rotation of D-brane. So it would mean that we can have phase, like a bound state of all D-branes, which corresponds to black hole. Or we can imagine gas of D-branes. When they are separated, they are not interacting with each other and they can fly away. And this is the state we want to study. So we have to single out this kind of state. And empirically, we can see that. So if we start with we choose a bound state or configuration with the small eigenvalues as the initial state, we can see such bound state exists as a metastable bound state, and it becomes more and more stable at large n. In string theory side, when we set GS to be 0, which and if we just use a supergravity, as far as I know, there is no instability of black D0-brane. And which would mean that if we take large and limited matrix model side, such flat direction would disappear dynamically. And numerically, what we can test is if we take this trace x squared divided by n as y direction, if some eigenvalue becomes large, of course, this quantity diverges. Okay, so if it doesn't grow, it would mean bound state is stable.
But at non-zero temperature, there are no flight directions.
You mean because of the finite temperatures, so these
are always working at some small temperature.
Yes, and the black hole can emit the D0-brane.
Yeah. And that the D0-brane has a finite energy, so it can actually fly to too far. I think it doesn't come back.
What are you plotting here?
And here, so this is actually cartoon, but we get this kind of plot. So in this direction is trace x squared divided by n.
What's the energy?
Integral is time. Average around the imaginary time. So what we calculated is a trace x squared. So we have imaginary time. So x squared of x is a function of time. This Euclidean time. So we can calculate this quantity and integrate over t. And I just divided it by n so that this is order 1 quantity into Fuchs counting.
And where is the dependence on beta?
Oh, yeah. So this integral is from 0 to beta. And this t can run from 0 to beta. And if you want to...
The answer should depend on beta.
Yeah. So this is about the specific, one specific temperature. Oh. At each temperature, we can draw this kind of a plot. So imagine that we fix t to, we say, 0.5 in the unit of lambda.
This is the expectation value for x squared?
No, so this direction is Monte Carlo time. So
the y-axis.
Y-axis is not expectation value. So here I said Monte Carlo time. It means in Monte Carlo simulation, we make a configuration after configuration, right? It's the first configuration, second configuration, third configuration. That's Monte Carlo time. And then we started with x equals to 0. Okay, and we plotted how value for each configuration changes. So this is for the history. And for n equals to 4, first it grows, and we see kind of metastable behavior, but it will diverge. Depending on temperature, even for n equals to 4, we can see stable simulation. But in some temperature, we see this kind of behavior. And if we, in general, if we increase n, we see longer and longer metastable.
Presumably those are smooth curves. You've smoothed over the fluctuations in the Monte Carlo.
Of course, there is actually, in actual simulation, there is a fluctuation like this. Yeah, and question?
Yeah, there's like this plateau that, you just mentioned that.
Yeah, this is a plateau. Yeah,
that is increasing with increasing n. Like, so if you were to take like n to go to infinity, we'll expect this.
For what we expect is it just to continue forever.
Okay.
Yeah. But it seems that stability increases like exponential n. So when n is like 30 or 40, during the reasonable simulation time, like 1 month, you don't really see instability. But that depends on temperature. Yeah. And as I said, actually we see this kind of fluctuation. So this is a black hole. This is picking up flat direction. And maybe some of you already have seen this famous plot, which is a comparison of Japanese stock index and the American stock index. And many people would have thought that Japan was going through 30 years of recession. But actually, we are simulating black hole, So this kind, if we pick up this kind of population, we can study black hole, okay? And the Americans cannot really study black hole, Now it's around here, so it's just a gravity gas. Okay, so this is what we want. Okay.
Can you explain why there's no decay? Why is it so?
Intuitively, so one intuitive reason is as follows. Imagine that you have a bound state of all the N and B branes, and they're connected by strings. They are sitting nearby, so a lot of open strings are excited. So if you have an N by N matrix, all the values are non-zero. Just put some. And imagine that one of the D-brane is emitted from here. It would mean you have something like 0, 0, 0, 0, and something here, and something here. Okay, and once such configuration appears, this eigenvalue can go infinitely far. But when one of the eigenvalue tries to escape, in order for this to happen, many entries has to become zero simultaneously. And that's entropically suppressed.
This argument might make you worry that Hawking radiation would be exceptionally slow, which is not the case, of course.
And that's a very good question, and it should be related to energy scale. And here we are talking about black D0-brane, where, and this is a kind of emission of a massive object, the D0-brane.
It's the emission of a heavy objects.
Yes.
The light objects are feeling a kind of potential that brings them back to.
But I think if this matrix model can also describe a small black hole in 11 dimensions, then what you say is a concern. And somehow there must be complicated dynamics, which allows much faster. So here, what I said is, so n of them has to become 0. And such process is entropically suppressed by factor exponential n. But n is, like mass is n squared, mass of black hole is n squared. So if it were Hawking radiation, it has to be power suppressed instead of exponentially suppressed. That's a very good point.
So sorry, is this like a 0 plus 1 dimensional version of a big black hole in ADS that doesn't evaporate? And the process you're talking about is just like a low dimensional phenomenon that is breaking up into smaller things, and that's not a.
Yes, you're right. And I will want to mention counterpart of small black hole later. I think I spent almost an hour, so I have to go a little bit fast. But anyway, so there are two papers. Okay, so in 2016, these people worked hard. In 2022, these people worked hard. And this is lattice action. And in 2016, we had a very big machine in California, which is called the Vulcan. And I think this is the origin of the name. I don't know why they used this name, but this machine is removed in 2019, so you cannot see it anymore. But in 2016, this machine was working hard, so we could use it. And typically, we could use like 200 to 4,000 cores in parallel, which is rather modest compared to lattice QCD. But we studied the various values of n, and the various value of temperature, and the various lattice sizes, and in total, all the 100 parameters. So each job is not too big, but the total resource we spent wasn't too small. So I thank American taxpayers for this. But I think I was paying tax to the US at the time, so maybe I shouldn't tax too much. Anyways, so we studied, say, regarding n, we studied n equals to 16, 24, and 32. And we studied various lattice point, and we extrapolate the result of infinite n and the continuum limit. And those are the data points obtained that way. And these are the fit result in a previous one from 2008 and 2015. And this is a new fit result, and this is supergravity. And in this fit, leading term is supergravity, and these corrections corresponds to alpha prime correction, alpha prime 3 and 5. Okay, so so far so good.
I'm still not clear on something. What you do is you create an ensemble of configurations.
Yes.
And you claim that the configuration that the computer spends most of the time with, the configuration with the D0-branes are near each other.
Yes.
And
when this kind of thing happens, we stop the simulation and we don't use such configuration. We use this kind of configuration.
So what we have in mind is that this is an approximation of some well-defined object that you're computing.
So maybe you're saying that in large n limit, it's well-defined because it becomes totally stable.
Well, you have a machine with finite n, a billion. Is there, which is much bigger than what you have. The expression that you compute, is it an approximate value of some expression that is within it roughly? Let me restructure the sentence. Is there an exact quantity, finite large n, that your computer calculation approximates?
So you're asking if we can define the energy of a metastable state precisely.
Well, whatever you compute something,
yes,
which would be an approximation for something. What is it an approximation of?
So we are picking up metastable configurations and we are calculating the average energy of that system, energy of a metastable bound state. And the metastable bound state become completely stable at large. That's our hope.
Can you write a formula for what it is that if you had an infinite amount of computer time, finite but large n, this is the answer that you think you will get?
They're discussing something that's not rigorously defined.
That's exactly my problem.
Yeah.
My problem.
Well, it's like discussing the energy of an unstable state.
That's right.
You can have a very long-lived state.
Yep.
It's not, energy isn't exactly defined, but it's defined to incredible precision, and you can calculate it to big precision with the right computer simulation.
Yeah, but I'm questioning whether I know exactly what you mean. There's a well-defined, there is a definition of the.
So for example,
I'm not convinced this thing will be true.
For example, imagine, so then
to define it is to find a point in the
so if
green axis, of the green axis. That would be a well-defined.
I think there is one way to define, give a precise definition, which is not, which should give the same large n answer, but it's not, it can be slightly different from what we are doing. So imagine, so eigenvalues of x are in the location of D-brane, okay? And we introduce some box. So we introduce a cutoff for eigenvalues of x and put the D-branes in a box and fix this box size and take large n limit first. Then even at finite n, this energy is well defined. And I think as n becomes larger, result is exactly the same as what we are doing. And in the case of linear matrix model, we have a flux parameter here. If we fix mu and n send to infinity, first take this limit and then send mu equals to 0. This is similar to this limit. And in this limit, I think everything is well defined. And the value of what we get should be the same as the larger limit of this quote unquote energy of metastables.
You see, if your evolution that you plotted there is Lorentzian time evolution, then, so when you had this plot, at some point it takes off.
This is Lorentzian time, but this is not, yeah.
Okay. If this had been Lorentzian time, I would say, okay, I'm in some metastable state, I'm there a long time, and like you simulate. But that's not what you do. Time is elsewhere in this cover.
This time is not really computer time, yes.
Yeah, so the fact that you spend a lot of time there in the computer does not mean that you're really in the metastable state.
No. That we spend the time here, and we can collect sufficiently many configurations would mean that there is a metastable state. Yeah, that's true. I think it should at least should correspond to say approximate minimum of free energy or something like that. That itself is okay, I think. And in order to give a mathematically precise formulation, we can take this kind of definition. And actually, this is what like Toby Wiseman and Simon Patel worried back then, and this is what they claimed. And so partition function of the FSS matrix model is divergent in literal sense. Oh, anyway, so we had the various energy. So we did simulation for fixed n and fixed each n. For each fixed temperature, we studied the various n and the various lattice size, and we did continuum and Radian limit. Okay, and we do that for various temperature. And so we have a various data points, so we can do numerical fit. And first, if we have too many parameters, we can fit. If we have 5 parameters, we can. With the 4 parameters, we can fit the elephant, and with the 5 parameters, we can move the nose or something like that. So we shouldn't introduce too many parameters. And the 3 parameters fit looks appropriate. So like these powers, so this is supergravity and alpha prime correction. These powers are prediction from string theory. And the string theory also tells that this A should be 7.41. And expressed variable B and C are not known. So just do 3 parameter fit and see if this A becomes 7.41. And the value we got back in 2016. And in 2016, this specific result is to this paper, I added 1 or 2 more data points. But anyways, what we got was 7.33 plus minus 0.35, which is in good agreement with this. So this is a good test. And then, these are not known from string theory side, but this fit result would give a prediction from a matrix model to string theory.
Sorry. Could you, why is 4 parameters too much? Like, do you don't have enough data?
The number of data points we have is how many, in this case, 1, 2, 3, 4, 5, 6, 7. And if we introduce, so you don't want to use the 2 high temperature. So I added 1 or 2 points here, but we had only 6 or 7 points. And if you have a 4 parameter, okay, you can fit anything.
Do you have any estimate for coefficient of 1 over n squared direction? Or?
Yes, we also did that, but I didn't prepare the slide. So later I can show you the number from our paper. And 1 minor correction and 1 minor squared seems to be also consistent with the string theory. So here I only prepared the slide for alpha prime correction. And here, so we don't want to introduce 4 parameters. So we use these fit ansatz. Okay, so here we assume that the difference of the power is, what we know from string theory. And we fix here, and we have the 3 parameter. And this P should be 4.6. This is a prediction from string theory. And then our fit gave 4.6 plus minus 0.3. So it seems to be nice. And of course, if we have more data point, maybe we can do even better fit without introducing such, if we reduce the amount of input from string theory.
Is anyone trying to compute the B parameter in string theory, or why is it so hard?
I think this is in principle doable, but it's immensely hard. You need detail. You have to know detail about Ramon sector or something like that.
It's hard to the 4th correction.
Yeah, whatever.
In principle, there should be doable.
Yeah, but and a few people say okay, I can do, and rather respectable people say that, and I don't hear anything from them after that. So I imagine I can give you the name after that. And now, it's broadcasted. Okay, so, but anyway, so here fit seems to be good, but still the difference is like 30% of the result. So we wanted to add a few more points. And these people worked hard and added these 2 points. And the important thing, which is almost trivial in this respect, was that we shouldn't use BFSS, we should use BMN, okay? And BMN matrix model is a one parameter deformation to BFSS. So this is additional part, okay? And there's one parameter mu, which looks like mass term. And this corresponds to some constant background flux. And this model has interesting on its own, but for here, I'm just using it to tell the flood direction problem. So BMN matrix model is a supersymmetric deformation of BFSS, and flood direction is lifted because there is mass term. But the flood direction is lifted, but a lot of new vacuum, which are called the fuzzy sphere, appear. So still we have to carefully choose trivial vacuum instead of fuzzy sphere vacuum. But we can do that monitoring the eigenvalue of X. And if we start with the trivial configuration corresponding to trivial vacuum, this mass term tells the flood direction rather well. And we can use a much smaller n without suffering from a flood direction too much. And the concern is that this mu changes energy a lot, but actually finite mu effect is very small at when mu is smaller than 1. And the value we use is mu equals 0.5. And in supergravity limit, Costa, Greenspan, Penedones, and Santos gave some estimate, solving using some numerical relativity. And their conclusion is that this black solid line, which is for BFSS, shifts only a little bit. And for alpha prime correction, we don't precisely know how much shift is expected, but maybe we can just hope shift is more or less the same. Okay, so we used mu equals to 0.5, where we could control flood direction, and we got this point for t equals to 0.3, and this point for t equals to 0.25. And it seems that the fit we obtained back in 2016 still works even in this temperature range. And so supergravity is rather precisely reproduced. And this is a plot of, this figure shows the values of n and the number of lattice points we used to get this point, okay, 0.3. And we studied n from 10 to 40, and the lattice size from 24 to 129. And using this point, we obtained the infinite n and the continuum point. And this color shows how much these simulation data deviates from a fit surface. And of course, if all data points come on top of fit surface, something is wrong. It should be somehow distributed near the fit surface, and the difference shouldn't be too big. And all data points are sitting between 2 sigma distance from a fit surface, so this fit is not that good. Anyway, and we also added a few more points with a smaller size of. So for these points, we didn't have too very big data, so the quality of the points are not too good. But it seems that even at higher temperature, BMN matrix model with the small mu and the BFSS model give you almost exactly the same answer. Anyway, so I spent more than an hour, so I think maybe I should wrap up here, or maybe I can continue, I don't know. Maybe people who are still have energy can remain, and maybe—
How long do you think?
Maybe I can spend 10 minutes. Maybe I can try 10 minutes. Okay, so far we studied the confined phase.
We should finish and then—
Finish and then continue, yeah, that's probably easier.
The way of doing this tea.
Then finish and get tea and then start again. I don't know.
But the people who want to leave can leave.
Okay, yeah.
How do we do the following? Let's protect the speaker.
also ask 3 more questions, so this will go.
I guess I bet it's one of those here.
You can wrap in 5 minutes.
Okay, let me try. Okay, so here so far we saw the confined phase, and actually we found this, which is clearly different from this one. And I want to discuss the meaning of this one. Okay, this is what we found.
The BMN model or
no, it's BFSS. So this is so for n equals to 10 and n equals to 16, we for lattice 48 lattice point. Okay, so we plotted how Polyakov loop and trace x squared changed. So trace x squared is roughly corresponds to the typical size of eigenvalue. So if this quantity diverges like this, this would mean simulation is picking up flat direction. So in this case, we started with x equal to 0. It came up, but the metastable state sets in, and then eventually flat direction picks up. In this simulation, we didn't pick up a metastable state and flat direction. But the Polyakov loop is fluctuating at a very small value. If we take the confined phase, actually the Polyakov loop has to be around 0.5. And the small Polyakov loop would mean confined phase. And this is equals to 0. So we are very much confused when we found it. But if we take a continuum limit for each fixed n, okay, energy goes to 0. If we fix n at each fixed n, if we take continuum limit, energy divided by n squared is consistent with 0. So of course, in large n continuum limit, it should be 0. And if we do the confined phase, the value we expect from this supergravity formula is 0.08, which is around here. So clearly, this is clearly we get energy which is much smaller than this and consistent with 0. Furthermore, if we plot if we take large n limit of a Polyakov loop at each fixed lattice size, we get 0. And if we take a continuum limit, continuum large n limit, of course it should be 0. At this temperature, 0.2, Polyakov loop should be around 0.5 if we just extrapolate from a higher temperature. And we saw this at mu equals to 0. So I say the flat direction was a problem, but in the confined phase, flat direction was a problem, and we needed finite mu to tame the flat direction. But somehow we found confined phase, and in confined phase, even at when mu is 0, we could simulate the system rather stably. So this point seems to be confined phase, and this is mu equals to 0. And as you said, at the finite mu, we expect a confined phase. But at this data point, actually we saw frequent turning between the confined phase and the confined phase. And we discarded the confined configurations. And that's a reason, error by speed. It wasn't very easy to tame the tunneling between confined phase and the confined phase. But these correspond to equal to 0.5. And if we believe the analysis by Costa and collaborators, critical temperature at mu equal to 0.5 should be around here. And we don't really expect frequent tunneling here. So, but when n is not very big, we see significant correction to supergravity, it seems. And I want to give you somewhat speculative interpretation for this confined phase, which is consistent with our observation.
To go back, you find it finite n or infinite n?
So it's at each finite n. So at infinite n, we should this plot itself. This point is infinite n and continuum. Yeah, but at each fixed n, we can see sufficiently stable metastable state.
A related question. So this type 2 supergravity, at the deep infrared, it breaks down.
Yes.
The electron goes up.
Yes,
So
yes.
Are you holding that definite one?
And if you take infinite, but if you take infinite in the limit, that point, this supergravity should be valid all the way up to 0. So the point where the atom blows up goes to 0 temperature.
You are in the large limit or what?
In the large, so this is, so from a matrix model side, we got this point as a large n result. But if we just apply large n, for the large n limit using the supergravity based on your paper with Farn and Shimon and Kobe, then supergravity should be valid all the way down here. So there's some clear deviation. But
confined phase, we just the bound state that we expect to have.
It's a bound state of, but both of them are bound state of eigenvalues. Both are bound state of eigenvalues.
Do you
but
have any interpretation for this? Is it like, could it be like a fuzzball, like it's horizon peak?
I want to try, I want to give you some speculation. And if you are happy with that, that's fine. If you're not happy, we can discuss further and maybe we can find better interpretation. And this is from a paper by Sunny and Juan and the collaborators. In this plot today, in this figure, they show low n in this direction, log of energy in this direction, and say at the lower energy, M theory should appear because the atom at the horizon increases if energy becomes smaller. And then seen from black hole, 11th dimension opens up. Okay, and if 11th dimension is not too big, you would see something like 11th dimensional black string. But at some point, Gregory-Laflamme instability along that M3 cycle should take place, and you should see 11th dimensional Schwarzschild boosted along the M3 cycle. But the important thing here is this is energy and not necessarily temperature. Okay, and usually low energy is low temperature, but if specific heat is negative, low temperature, I don't know, low energy may be high temperature. That's the point I want to emphasize. Okay, anyway, so they say, so starting, this is basically type 2A. This direction is the M theory cycle. And if we see something like uniform black string, it looks like, from 10-dimensional point of view, this is just 10-dimensional black hole. But maybe localized black hole can appear at low energy, and the M3 black hole should appear. Okay, this is what is framed up in 1998. Okay, and to reconcile that paper and our numerical observation, I want to give you some speculative picture. So this is what we expect from duality. By using duality in fourth large n limit, where t is fixed and n is sent to infinity, we expect this. So at any non-zero temperature, the confined phase is favored, and the energy goes up like this, and the particle flow starts with 0 and then approach to 1. Okay, but I want to say maybe there are two minimum of free energy. And maybe there's a confined phase where E over n squared is 0 and the particle flow is 0. And at any temperature, this is global minimum, this is a global minimum, this is local minimum. And there is some free energy maximum sitting in between. And it's getting more speculative. As you say, if we start with at finite n, when n is not too big, if we go to smaller energy, at some point the atom blows up. Type 2A discretion doesn't work anymore. But then like M3 black hole should appear. And if that has negative specific heat, 11-dimensional Schwarzschild black hole can be free energy maximum. And then at some point, 11-dimensional graviton gas sets in. That can be confined phase. And this temperature approaches to 0 as n becomes large. And I don't know how this highest temperature of graviton gas scales, but it would be natural to think this actually blows up at infinite n. And I want to claim that. So this free energy minimum is dual to type 2B string, type 2A string. And this minimum and this free energy maximum would be M theory. This is very speculative. But let's get intuition from 4n equal to 4 on 3 sphere. It's kind of similar. So this is a famous phase diagram based on proposal by Euclidean. So this is energy versus temperature. And at low energy, we have a string gas or graviton gas. At some point, hydrogen string sets in. And then if a hydrogen string becomes larger, description as a 10-dimensional black hole comes to. And the 10-dimensional black hole is localized on S5. And the ADS5 plus S5 is like a gigantic box, but this box looks like a 10-dimensional flat space. So E is n squared times t to the minus 7. T to the minus 7 is a temperature dependence of 10-dimensional Schwarzschild. If it's a 4-dimensional black hole, it's t to the minus 1. And then at some point, this black hole becomes large and completely fill S5, and there is a phase transition. And then ADS5 Schwarzschild becomes good description. And then at some point, the space heat turns to positive. And there are two free energy minima separated by free energy maximum. And Horowitz found that if we believe duality is valid, even at a stronger coupling, if two-foot coupling the lambda increase with faster than some power of n, then actually hydrogen string disappear, and this small black hole and the graviton gas can meet. And this temperature where two phases meet diverges when n goes to infinity. And in a canonical treatment, so they say that this is free energy minimum, this is also minimum, and there is a free energy maximum separating these two minima. And the Hawking page is around here. Above Hawking page, this is a global minimum. Below Hawking page, this is a global minimum. And if we send n to infinity, it comes like this. And if something similar is happening in a BFSS, we can explain our numerical observation. So this point would go to 0 at the large n. And I don't know precisely how this temperature scales, but it would be natural to think this diverges. And this critical temperature also goes to 0 at the large n. If that's the case, paper by Itsuaki Marudo-san and Shiniakirovich and our numerical observation are consistent. This is one way to resolve the tension. And if it were the case, then between critical temperature and this T1, then type 2A black D0-brane is a global minimum of free energy, while the 11-dimensional graviton gas is, which is confined phase, is a local minimum. And the below critical point, this is global minimum.
Is this a large n or infinite?
So again, in infinite n, this T1 goes to infinity, TC goes to 0, T2 goes to 0. But this is a matrix model, so unless we take large n limit, we cannot precisely define phase transition. But I'm pretending as if n is large and the phase transition is good enough. So this is large but finite n. And the phase transition is approximate. Yes, I don't know, this may be very speculative, but gravity side is not completely known. So if we understand gravity side better, maybe we can have better understanding regarding our observation. Anyway, so I wanted to say Monte Carlo is a powerful tool for string theory. And by using BFSS and BMN matrix model, we could do very precise test of type 2A matrix model duality. And rather unexpectedly, we found confined phase equal to equals to 0. And I made some speculative proposal, which relates confined phase and M theory. And if this is if it were true, it's interesting because we might be able to study 11-dimensional black string and black hole using holography and numerical simulation. But I have to say better understanding of gravity side is needed in order to understand the numerical data more precisely. Thank you very much.